Alright, hello. We're going to continue with our discussion of Chapter 11, and this time we're going to move on to the conservation of energy. So we talked about the different types of energy in Section 1, mainly potential and kinetic energy, and now we're going to talk about how energy is conserved. So the law of conservation of energy says that in a closed, isolated system, energy can either be created or destroyed. It is conserved. So we need to have a closed and isolated system in order for this law to kind of be in effect. Energy can change from one form to another, but the total energy of the system is going to remain constant. And so that's what we're going to talk about in this section, is how we convert between mainly kinetic and potential energy, but the overall energy of the system is the same. Alright, so we've mainly been working in terms of mechanical energy, and the main forms of mechanical are kinetic and potential. And so in order to conserve energy in a closed, isolated system, we would add up the kinetic and potential energy of the system. If there are no other forms of energy present, and so in a lot of these problems we're going to ignore friction and other ways that we can lose energy or convert it to other forms. So if we have no other forms of energy present besides kinetic and potential, then the overall energy of the system is equal to the sum of the kinetic and the potential energy. So we can also have conservation of purely mechanical energy, the two forms being potential and kinetic. And so if we have conservation of mechanical energy, this says, very similar to how we conserve momentum, that the kinetic energy before a collision plus the potential energy before some sort of collision or action is equal to the sum of the potential and kinetic energy after the collision or action or whatever it is. And I can see that this E should be capital. Okay, so very similar to conservation of momentum. So for example, if we have a 10 Newton ball that is falling from 2 meters, we can calculate its initial potential energy by taking its mass times its acceleration due to gravity times height. Well, m times g is also equal to force, right? Or weight, because force is mass times acceleration due to gravity. And so that's where we're getting the 10 newtons times its height, which is initially 2 meters up from our reference point, which in this case appears to be the ground or the bottom surface. So if we multiply those together, we get 20 joules. Remember, these are versions of energy, and the units of energy are joules. As the ball falls from the 2 meters, it's losing potential energy, but it's gaining kinetic energy, because remember, the total energy has to be conserved. So if it loses some potential, then it's gaining some kinetic. We talk about initial kinetic energy. If I'm just holding the object at 2 meters, it's not moving, and so its initial kinetic energy would be 0. And so the overall energy of the system, initial, would just be my potential energy, which is my 20 joules. So let's say that we take a snapshot of this object at 1 meter. So it's fallen 1 meter and it still has 1 meter to go. We can calculate the potential energy at this point in time by taking its weight, or its force, which is still the 10 newtons, times the height from the reference point, which is now 1 meter. And so now it has a potential energy of 10 joules. Okay, well, it's obviously lost some potential energy, but we know our total still has to equal the 20. And so if my potential energy after, and I'm going to count after as just that point of 1 meters, then I need to find my kinetic energy. Well, I know that kinetic energy is equal to the total minus the potential at that point, and so it's 20 minus 10, which just gives us 10 joules of kinetic energy at that point of 1 meter. This would occur in roller coasters, pendulums, anything where we've got initial situations and final situations. And we'll look at problems where, if you have a skier or a roller coaster, you start at this tall hill, you may go down and then they want to know the energy at a lower hill height. So really we're just taking those 2 points, and it doesn't really matter what happened in between. And so we'll do some practice problems with that. Well, we can, in the real world, lose mechanical energy to other forms of energy. So overall, energy is still conserved, but these are forms of energy that we don't normally calculate in this general type of situation. So we can lose mechanical energy to air resistance. Friction is kind of an overarching description, air resistance being one of the forms of friction. We can lose it to thermal energy, sound energy, so lots of different types of energy besides just mechanical, which mainly involve potential and kinetic. So for our purposes, we're mainly going to look at potential and kinetic and kind of ignore the effects of these other types of energies, but just keep in mind that in the real world, energy can be lost to these other forms of energy. Overall, it's conserved, but some of that mechanical energy is going to go to these other forms. Okay, so to solve conservation of energy problems, first thing you need to do is identify your system and make sure that it's closed. And this is how we're kind of controlling for some of the loss of energy to those other forms. Then you need to identify the forms of energy in the system. Mainly, like I said, we're going to look at kinetic and potential. And then you also need to identify the initial and final states of the system. So like we talked about with that roller coaster problem, if you have a large starting hill, and then they want to know, so you've got, this would be your initial condition, and they want to know speed or energy at a final condition, maybe at the top of a smaller hill. What happens here, not that it's not important, but we're only going to look at the initial and final states. We're not really going to look at what happens in between. So to determine if the system is isolated, yes to that question would be that the energy before equals the energy after. So when we're looking at like the difference in mechanical energies. Sometimes a system is not isolated, however, and this is where we have that loss of other energies. And so we need to add in what work is done to the energy before to get the energy after. And we'll do some examples with this. If mechanical energy is conserved, then you also need to decide on the reference level for your potential energy. Is it going to be the ground, or in an example such as the skier or roller coaster at two different hills, maybe you want to choose this as your reference point since we're only interested in initial to final conditions. Okay, so and a lot of times when you have transfer of energy, we have a collision. So we can talk about two different kinds of collisions, and we've kind of already referenced this a little bit, especially momentum and in section 1. So what you need to do is find the motion of the objects just before and just after the collision, and those would be your initial and final conditions. If the system is isolated, this means that momentum and energy are conserved. We can't predict about kinetic energy, and we'll talk about why in a minute. But if it's isolated, that means that momentum and energy are both conserved. So there are two main types of collisions. In an elastic collision, this is where kinetic energy doesn't change. So these would be collisions between hard elastic objects, billiard balls, steel, glass, hard plastic, things where the objects are not deformed after the collision. In an inelastic collision, this is a collision in which kinetic energy decreases, mainly because the objects are either deformed or stick together after the collision. So energy gets converted to a different form, which is why kinetic energy decreases, and these would mainly be collisions between soft or sticky objects. Okay, so we said that if the system was isolated, that momentum and energy would be conserved. Momentum is almost always conserved in a collision, whether it's elastic or not. Energy is only conserved in elastic collisions. So the momentum is what stops the objects in the collision, but it's the energy in the collision that can cause the damage. So the more energy you've got, the more damage you're going to have as an effect of that collision. So let's look at some different examples. So first we have two billiard balls. These would definitely be an elastic collision. The objects are not going to be deformed after the collision. Momentum is going to be conserved, and because it's elastic, energy will also be conserved. So we'll be able to take our potential and kinetic before the collision and equal that to our potential and kinetic after the collision. Let's say instead of billiard balls we have two humans, so two ice skaters. This would be an inelastic collision. So they're typically going to either stick together after the collision or, something is going to be lost in different forms of energy. Momentum is still going to be conserved, but kinetic energy is going to become half of the original because let's say that they collide and then stick together and fall down. Now we have lost energy to other forms. Okay, so we are going to go over these practice problems together, and then here is the homework along with the answers if you would like to start working on that. Have a good day.